we'll proceed from where we left. Okay. So in the previous session, we were looking at the term called as the momentum, and the momentum is defined as, it's a term that actually brings a concept of direction in which the machine is going to learn from all the past weight updates, right? It's not going to update the weight instantaneously, and it is going to perform the weight update after considering all the previous weight updates. And there is a factor beta which is used to define what extent the previous weights are supposed to be used for the weight update. Okay, so that's the momentum, and we have seen that the momentum gives you the stability as well. For the training, the weight updation, it's not only just bringing into one direction, it also gives you the stability, right? We had seen that when we try to run the code, right, we understood that it gives you the stability as well. Okay, and the comparison with the normal SGD method, there is increase in the learning rate, in the sense instead of providing 1 lakh epochs, 10,000 epochs are sufficient to get the similar, right, the similar learning rate, right? So this is what we had studied earlier, and now we move on to the next topic, and this is called as a cost function. Okay. Right. Now we'll bring the new term called cost function. Basically, this cost function is going to affect the learning rule of a neural network, right? So basically, the cost function is originally termed for a mathematical concept called as optimization. Okay, in a mathematical optimization process, right, we use the word cost function several times because it was first coined for that purpose only, right? So optimization theory is a part of mathematical analysis, right? But in order to apply the cost function to the neural network, I don't have to, there is no compulsion that you should know the whole concept of optimization theory and how the cost functions are used over there. It's not required, we can directly use it here. Okay, now let's try to discuss what is a cost function, right? So basically this cost function is directly utilized wherever you are performing the supervised learning. Okay, so this is used for the supervised learning, right? In any of the machine learning techniques where you apply supervised meaning you provide certain input and you teach the machine that, okay, this is class 1. So next data you give and you tell the machine that this data belongs to class 2. So you supervise and you check that whether machine is learning or not by doing a calculation such as error. So you see in these methods what we are studying now, they are all the supervised technique, because always you give a data point and you give a desired output as well, because okay, this is the input, this belongs to class 1. If the machine has learned or not, right, how do you compare? You check with the calculation of error, right? You do the error calculation and you verify, okay, whether the machine has learned or not, right? So this is called as a supervised learning. So we are doing the supervised learning always so far. So this particular cost function is actually directly related to the supervised learning techniques of neural networks. Okay, so far what we discussed, we are applying the supervised learning to the neural network, and the whole process of adjustment of the weights is to reduce the error of the training data, correct? So error calculation was there, our intention was to minimize the error. Error is minimum means yes, machine has learned. So you see, earlier I told that the whole concept of the cost function was used for optimization. Now actually in what we had been studying so far in terms of the neural network, we were actually solving the optimization problem only, but we never used optimization word as it is, because we always looked at the error and we wanted to minimize the error. So minimizing the error itself was our optimization problem. We were actually solving the optimization problem only so far. Okay, fine. So considering that, the measure of neural networks error itself becomes the cost function over here, right? So what is the cost function, right? So cost function is basically, right, whatever you wanted to minimize, right? So that looks like a cost function for you. So in our neural networks basic problem of supervised learning, right, the measure of the neural networks error becomes the cost function. So let's just make a point of that here, right? So the measure of the artificial neural networks error itself becomes the cost function. Okay, so that is a cost function. So greater the error of a neural network, higher will be the value of the cost function, right? So indicating that more error, more cost, lesser error, lesser cost. So, right? So our intention is now, if you want to say that I just want to make the error as minimum as possible, the cost function related to the error should also be minimum, right? Okay. So greater the error, if the error is bigger, this is going to imply that higher value of the, I'll just write CF indicating that this is the cost function. So I'll write in bracket, this is CF. All right. So now again, going back to mathematics, right? If you look at the concepts of optimization, the cost functions are basically of two types, right? We can write the cost functions in two different ways. Let me directly write those equations over here, and let's try to apply the same thing to our neural network later. So first cost function is, I'll write in terms of the neural network parameters itself. The cost function is denoted by J. Right, the first cost function I can write, right, related to the neural network is I is equal to 1 to m half of, even the half I can write out outside the summation, that's fine. Half of this is di minus yi the whole square. Call this as equation number 1. So here the yi is the output of the neural network, the di is the correct output of that, and m is the number of output nodes. Let me just write that. Okay, so where di is the desired or the target value. So the yi denotes the ith output of the artificial neural network, then m is the number of output nodes, or m represents the number of neurons present in the output layer. So previous example which we considered had one output layer, there was one output layer, and inside the output layer you had only one neuron. So m becomes 1 in the previous example, right? But it can be generalized to any other value like this. All right, so let's move further. So that's the first equation, right? Let us try to look at this equation. What's the meaning of this, right? So you see this particular equation. Let's show you the equation once again. So this equation, what we are seeing here, is the sum of the squared errors, right? So you see di minus yi is the error, and if you take a difference of desired and the current output, you get an error. So what you have inside the bracket is an error term. You have a square, right? So you are squaring it and you are taking the sum of all such errors and dividing it by 2. So this cost function is the square of the difference between the neural network's output, that is yi, and the current the correct output, that is d. Right? So you see that if the output and the desired output both are same, no error, right? And if at all you have the d and y, they are different, more the difference, more is the error increases. So you see that as per our definition, right, we said that we want to develop the cost function in such a way that error is greater, implying that higher value of the cost function. So the j value increases as the d minus y increases, right? So basically this equation number 1 is, right, all about, it's a cost function. It is defined in terms of the square of the difference between the yi and di, right? So equation number 1 is nothing but the squared difference of d and y, right? There is a square and definitely it's a addition, so there is a sum, right? So let's look at the cost function now. So if at all I just want to plot this function, how it should look like. Okay, so let's make an analysis first. So let us assume that the d minus y, that difference, is positive. Okay, if the d minus y is positive, what should happen to half of d minus y the whole square? Is it positive or negative? The d minus y difference is positive, so its a square term is also positive, right? So d minus yi whole square is positive term, half of that is also positive. So when the d minus y is positive, my result is positive, the error term is positive. Okay, at the same time, what happens if d minus y negative? When the d minus y is negative, its square is once again positive, correct? So you see, irrespective of whether the d is larger or y is larger, you are going to get positive answers only, correct? So let me try to plot that, right? So if I try to plot that graph of this particular function, you can see that it's going to look like this. This is the cost function when we are trying to plot the cost function indicated by equation number 1. All right, so from this equation as well as the graph, it is very clear that the cost function, its value is proportional to the error. So relationship is pretty straightforward and intuitive, right? I don't think there is any other explanation required, because d minus y increases, e increases, whether it is on the positive side or the negative side, it doesn't matter, because anyway I have a square over there. So it's the square term, right, makes the negative terms as positive terms. So that's why e is positive on both sides of the y-axis, right? So that is the reason why the graph takes this particular shape. All right, so earlier studies of the neural network employed this as the cost function to derive the learning rules. Okay, not only the delta rule of the older techniques, not only just that, but also the back propagation algorithm, everything used this itself as the cost function in the olden techniques, okay, so of mathematics, right? Let's move further. There is another, as I told, we have two different versions of the cost functions, right? So let's go for the updated version, right? The second equation corresponding to the cost function is this. The j is equal to, this is summation I is equal to 1 to m, I say flower bracket, this is minus of di into natural log ln of yi minus, this is 1 minus di into the natural log of 1 minus yi. Okay, so let me call this is equation number 2, right? This is the updated version of the cost function in most of our algorithms. All right, now let's see what is the speciality and why we actually had to update to this equation, right? So let us try to define one term. Anyway, there is a summation, whatever is there inside, I'm going to call that as an error function, because you see here the previous equation was the summation half of d minus y the whole square, right? We call this is e, so this is summation of error terms, correct? So I have to use the same logic over here. So I'll just erase this and let me say whatever is inside this, that is whatever is inside, just highlight, right? Whatever is inside this flower bracket, we are going to call that as the entropy function, right? So let's write that. All right, let's define the entropy function E, that E is equal to minus d times natural log of y minus, this is 1 minus d into natural log of 1 minus y. Right, now it becomes very difficult since there is a log function as well as a multiplication of d and 1 minus d with us, right? You see that it is going to be very difficult to analyze the whole function as simple as the previous one. Previous one was very straight, right? I understood what's happening. So irrespective of d minus y, it is positive always, I understood, right? But that is not happening over here because of the presence of the log function as well as the two different terms with the d and 1 minus d, right? So because of this, now what we have to do, let us look at this in detail. Actually, I can see that the term is made up of two, right? The whole equation is made up of two different terms. One is minus d into natural log of y, and the second term is minus of 1 minus d into ln of 1 minus y. Okay, now let's look at this, right, in terms of some condition. Let's apply a condition and understand what exactly is happening here. Okay, so let us try to understand one thing here. So the E becomes, now I'm trying to simplify, E becomes simply minus natural log of y, right, when d is equal to 1, right? Let me analyze this later. Let me write the complete equation. This is minus ln of 1 minus y when d becomes equal to 0. So just analyze, when d is equal to 1, this term is not there. So 0 into any term, that cancel, you just have minus of ln of y. That's what is here when d is equal to 1. Okay, if you put d as 0, right, so the desired value, if at all it becomes a 0, then this term is not there. This is simply minus of 1 minus 0, which is minus 1. Only this term comes into picture, which is minus ln of 1 minus y over here, right? So you can, now it becomes easy for us to understand, right? If d is 1, I get one graph. If d is the other one, I'm going to get a different graph, right? So the graphs that we are going to get as an entropy function is completely different for the desired value d is equal to 1 and a desired value d is equal to 0. Okay, now so due to the presence of this logarithm, right, the output y should be within 0 and 1 for sure, right, because of log is present. And the what you call as a cross entropy, the cost function, is often teams up with the sigmoid and the soft max activation functions in the neural networks. We'll see that later, but anyway, I just have to tell you this now. And right, let us see, the cost function should be proportional to the output error, right? So that is what we can see here now. All right, so let's just check this. So what is going to happen when d is equal to 1? Let me try to plot this graph so that we understand what is the shape of the graph. Okay, so if d is equal to 1, this is how the function is going to look like. All right, so we can see that the output y is 1, so the error d minus y is 0. Okay, output y is 1 when the error is 0. So you can see that error is minimizing, error is reducing when the y becomes equal to 1, right? So the cost function is also 0. In contrast, so when the output y approaches close to 0, that is towards the left side, error will grow. Cost function is also going to increase. So this cost function is proportional to the error. So we actually expected whatever cost function you write, it should be proportional to the error, right? So that's happening here when d is equal to 1. Now let us see whether the same thing is going to happen when the d is equal to 0 as well. So if I make d equal to 0, then the same cost function indicated by the equation is that it's a minus of ln of 1 minus y. So that term is what we are going to look now, how it's going to look like. Again, this is the graph corresponding to d equal to 0. So when the d becomes equal to 0, the curve looks like this. Again, if the output y is 0, right, the error is also 0, that is over here. Okay, error is 0, right, y is 0, right, y is my output. And as the error grows, as the y grows to 1, y comes closer to 1, error also increases, and you can see that error is maximum at 1. So again, we can see that the cost function is proportional to the error. So both the cases confirm that the cost function which we had defined using this equation number 2, is proportional to the output error of the network. So it's clear that, okay, we could define a different error function now, which is also increasing, right? Error increases with the error is going to increase means the cost function is also increasing. This is what was our basic requirement, and yes, we are satisfying that with our new function as well. Okay, now what is the primary difference between our first function and this function? The function number 1, if you look at the function number 1, that is basically it was defined in terms of a quadratic function, right? So the equation number 1 is a geometric increasing, right? So in other words, the cross entropy function is much more sensitive to the error. right? That's what was happening with the equation number 1, right, where we wrote it as the value is equal to the cost function was directly proportional to d minus y the whole square, right? So that was a fundamental problem, that it was very sensitive to the error. It's in the sense it's sensitive, but it's something like it's more sensitive than required. Okay, so that's our fundamental idea. And let's see if this moves further. In case of the second equation, it is not that much sensitive, right? So it is not that much sensitive, meaning that, right, you can see that, right, as the error increases, it increases or decreases logarithmically. It's a log scale, not a polynomial or a quadratic function. Quadratic function is, right, small increase in x increases the f of x by a drastic amount. That's not happening here, so that's the fundamental difference. Okay, so let us try to write this. So in equation number 1, the entropy or the cost function increases geometrically. So geometrically means it's like the progression will be geometric progression, GP, right? So why? It is because of the quadratic equation. So this is the quadratic equation, right? So this implies the cost function is it's more sensitive to the error, right? There is more sensitivity towards the error. So the learning rules derived from the entropy function, that is from the first technique, right, yields, right, a better performance because more sensitivity. It is recommended that we use the cross entropy driven learning rules, except right, some cases of regression. Other than that case, we expect to use all the functions which are based on the cross entropy. Okay, then let's say the cost function is clear for us, right? So now we have to apply the formula of the back propagation algorithm to this. Somehow we have to use this. So specifically our intention is that the calculation of the delta at the output node, right, is going to change slightly whenever I try to introduce the concept of cross entropy over there. Okay, so now let me try to write the stepwise procedure in the training of a neural network with the sigmoid activation function at the output node using the cross entropy driven back propagation algorithm. So I'll just write the steps now so that the points become very clear. Okay, so this is the side heading, the steps used to train a neural network with cross entropy based EBP, standing for error back propagation. So the error back propagation algorithm, we try to introduce the concept of cross entropy. Okay, let's see what are the changes. So let me give the step-by-step procedure so that this becomes easier for you to recall when required. So the step number 1 is that initialize the ANN weights. So normally we know that we are going to do it at a random procedure. You declare it as random, but don't go for a very large, very small values, in some medium range between say 0 to 2 or 0 to -2, right? Anything like that, right? Then in a second step, right, enter the input of the training data. We give the input, right? Normally what is the format of the input, right? That you try to give the input as well as the correct output, right? So enter the input of the training data to the ANN and obtain the output. So with the initialized values of the weight and the bias, you can simply perform what is called as the output calculation. Multiply the weight into x, get the partial output, give that to the next hidden layers, calculate the output, right, by multiplying the weights, and so on. Do this for all the hidden layers, and at the end you get the required output, right? So you get an output now. It's not a required output, you get an output. Then you compare it with the required output or the desired output to make some decisions. All right, so once this output is obtained, then you are supposed to compare, right? Compare this output, to the correct output. Calculate the error. That is E, and the delta of output nodes. All right, so how do you calculate error? Error is equal to d minus y, and for the output, right, we can assume that delta is equal to E. Now, so this delta of the output node should be propagated backwards and calculate the delta of subsequent hidden nodes in the next step. So this is the step number 3. So you can see that we are going to propagate the delta value of the output node in which direction? In a backward direction. And what I'm supposed to do? Have to calculate the delta values of all subsequent hidden nodes. So how do you represent that? EK, error of the kth hidden node, is W transpose into the delta, right? And the delta of the kth node, hidden layer, can be calculated as the phi dash of whatever VK into the EK, right? It's the same equation. So that there will be change only when we bring the concept of the cost function. Until there, everything will remain same. Okay, so let's proceed further. So this means we have to repeat the step number 3 until it reaches the hidden layer, which is next to the input layer, right? So I can simply write this. So the fourth step is that repeat 3 until all the hidden layers are completed. Until you complete all of them, repeat this. Now once this is done, that is fifth step, it's error back propagation. So use the delta values we calculated for each of the hidden layer, right? So use that to update the weights, right? And for the output layer, you can apply the delta rule itself, because delta is valid for that, right? So adjust the neural networks weights, right? What is that? What is the equation? First one is Wij is equal to the alpha into delta of the ith layer and the input from jth layer, and the Wij is equal to the Wij, this is actually the old value, plus the delta Wij. Simply we can apply this and calculate. Okay, now okay, we have to repeat this for until some condition is met. So the steps will remain same like the back propagation algorithm, right? So repeat step number 2 to step number 5 for all the training each and every training data has to be given, and step number 2 to 5 has to be repeated. That completes one epoch, right? So step number 7 is to define the number of epochs. How many times you have to do, right? Repeat the 2 to 6, right? 2 to 6 is repeated, right, until the artificial neural network is properly trained. So until and unless, right, the neural network learns properly to classify the problem, right, you will make sure that it's going to learn. All right, now let's come to this. The similar steps were written in the previous case, right? The error back propagation. So what is the difference? Definitely there is a question, what is the difference, right? So could you notice the difference between this method and the previous method? The back propagation is also very similarly, we had written the same 7 steps. I will just show you that, so that if possible you try to see. This is EBP process. Similar 7 steps were there, right? Repeat 2 to 5 until everything. So what is the difference? So can you think of what is the difference between this step and the previous one? Okay, no problem, I'll tell you that, right? So just look at the point number 2 over here and look at the point number 2 over there. Okay, only one very minute difference is there. Actually, if I simply see, it looks like an insignificant difference. The difference may look like, okay, what's the big difference among them, right? We may think like that. I'll just show you that. Okay, see the equation, the second step. I'm trying to highlight what I'm saying. Look at this equation, right? This is one part, right? Error is equal to d minus y, delta is equal to phi dash of v into the error. All right, that's one thing. That is the simple EBP. Right. Now I'll come to the EBP with the cost function and look at the equation number 2. Error equation is same, but the delta equation is different. Delta is simply delta is equal to E for the output node. So difference is only that much, right? So if I simply look at this, right, again now also I can ask the question, what's the difference? Simply instead of assigning, right, the delta is equal to phi dash of V into E, now you say that you are going to make delta equal to E itself. What's a big deal, right? There is big deal, and that's going to that is the concept we are directly taking from the concept of optimization in mathematics, which is going to help you to bring up the concept of the cost functions inside this backpropagation algorithm. All right, let's see now. Right, so I'll just write what's it, the difference, right? So I'll just write on the left side. This is what we are going to do in the EBP, the error backpropagation. We had the assignment of delta is equal to phi dash of V into E, right? So in case of the cost function based error backpropagation, you see that the delta is simply E. Everything else, complete algorithm remains same except one step, that is also in the outermost in the outermost layer or the output layer of the neural network. Only there we have this difference coming into picture. Other than that, nowhere you have a difference. Okay, everything else remains same. So if you look from outside, the difference seems insignificant, right? Actually, it contains a huge topic of the cost function based optimization in place. So most of our neural network training approaches of any deep learning technique basically apply the entropy driven learning rules. That's why they are actually going to attain superior learning rate and the performance. Already we have discussed about this. The performance is also going to increase because there is more sensitivity towards the error, right? Okay, now let's see how this is going to be very significant, right? So before that, let's consider a diagram, but let us understand one thing here. The key fact is that output and the hidden layers employ different formula for delta calculation, right? Because output layer is going to use delta equal to E, all right? But the hidden layers are not going to assign the delta as it is, right? Because there you calculate the delta separately. You see, for the hidden layers, delta calculation is still there, and that follows the older equation. Only at the output layer you have, right, a difference. Let me write the key point here. So the output and the hidden layers use different formulae of the delta value calculation when the learning rule is based on the cross entropy, right? And we use a sigmoid function as the what you call the activation function. Okay, let me show you what exactly is happening. Again, I'm trying to copy a diagram for our reference. So it actually shows both the output layer's delta calculation and the delta calculation corresponding to a hidden layer. Okay, so just consider this diagram and you can see that, right, this is the output layer and the output layer's error is directly assigned, right, as the function, right? So you calculate error is equal to d minus y, and that error itself is given as delta value of that particular layer. Whereas when you come to the hidden layer, right, you calculate the error, right, use the phi dash of the output of that layer, right, and calculate the delta value of this layer. So that is a difference. So this difference is the first part which we need to understand. Okay, next. Right. So if you are trying to use this approach, right, it actually uses what is called as a regularization, right, in addition to the sum of weights to the cost function, right. So apply the following cost function to the learning rule. Actually, when we do this, this is what is going to happen. There is what is called as a overfitting. In order to eliminate that, we have another part coming into picture, right? That is what we add to the cost function, so that it determines how much of the connection weight is reflected on the cost function. We bring a new term to this. All right, so that is, let me write the new equation now. That is, so the J could be equal to half of the summation I is equal to 1 to m. This was the original term, that is di minus yi the whole square. To this, let us add another term, that is lambda times half of the weight square. It's a magnitude, all right? So did the square. Otherwise, for the second equation which we considered, you can use this. That is summation I is equal to 1 to m. This was minus di natural log of y minus of 1 minus di into natural log of 1 minus I. Okay, plus the same term. Okay, I have to write a lambda first. So we can simply write lambda by 2. So this is simply lambda by 2 into w square, right? So lambda is the coefficient that determines how much of the connection weight needs to be reflected on the cost functions. You see, the lambda is going to determine that. Lambda 0.5 is half of that. Lambda is equal to 0.75, 75%, and so on, right? So this cost function maintains a large value when one of the output errors and the weight remains large, right? So cost function is large if error is large and the weight is large. So solely making the output error 0 is not sufficient to reduce the cost function. So what you are supposed to do, in order to drop the value of the cost function, error and weight also should be made as small as possible. That's what is our basic idea now, right? So to reduce the value of the cost function, we have to reduce two things now. What are the two things? First one is reduce the error as well as the weight. So you see, if the weight is larger, input into larger weight generates a larger answer. That's why you have a bigger error coming, correct? So that logic is makes sense, right? Very much sense, because you have a larger weight, it generates a larger output, maybe because of which you have a larger error. So reducing an error indicates that reducing the weights as well. So this takes care of that. So in order to drop the value of the cost function, right, both errors and weights are supposed to be controlled to as small as possible, right? Now you see, if a weight becomes small enough, associated nodes will practically get disconnected. Very small means there is no connection, right? Because the effect is less, because the lambda will control effect of the weight. Weight itself is small, so lambda will make it further small. So it's like you are disconnecting those nodes from this. So as a result, the unnecessary connections will automatically get eliminated and the neural network becomes simpler, right? So why did you bring the concept of reducing the weights as well? Is just because of this. All right, so I can write another point. This implies if the weights reduce significantly, this can be considered as, this implies that associated nodes are eliminated, right? I can write associated to that weights, associated whatever nodes we have, right? Those nodes are, we are trying to say that those nodes get disconnected. When such nodes get disconnected, this actually implies that all the unnecessary connections of the artificial neural network's hidden layers, right, all the unnecessary connections get eliminated. So when the unnecessary connections get eliminated, neural network becomes simpler. So you get simpler the artificial neural network. So for this reason, this the overfitting of the neural network can be improved by adding some of the weights to the cost function, and you try to reduce that as well. All right, so you see we brought a cost function into picture. Our ultimate goal is to reduce the cost function, but when you try to reduce these cost function, you are ultimately reducing the error as well as the weights of the neural network, right? So overall, the summary of this concept is that the learning rule of a neural network in supervised learning mode is actually derived from what is called as a cost function. And we can say that the performance of the learning rule and the neural network definitely depends on the selection of what type of cost function you are using. So the one which we had studied so far is called as the cross entropy based, right, technique, and this is going to, right, deal with the overfitting concept, as well as it's going to make the neural network simpler.